So in part 1 and part 2 we have discussed that signal flow graph, and here this is part 3 of this lecture, that is part 3. So here we'll continue that signal flow graph and we'll be solving two more problems to better understand that signal flow graph algebra. So here we take one block diagram. So here we'll take one block diagram. This is one example. So this is plus, this is minus. You have that error signal, and here you have G1, the transfer function. You have another summer. You have G2, another transfer function. G3, you have another summer here, and this is that output variable. And here you have one variable, that is Y2. So this is that feed forward path, G4. Here you have that summer. This is plus, this is also plus, and then we'll close this loop. Here you have that feedback path, and here you have another feedback path, that is H2. Now from here, so basically there are three loops. There are three loops, and this is a closed loop control systems, and we are trying to represent it by a signal flow graph. From there we will be finding what is the transfer function. So this variable is defined as Y3, this is Y2, and you have another variable, that is Y1, and these are the transfer functions. So suppose you have this transfer, this block diagram representation of a closed loop system. So now our objective is to draw or to present this closed loop control system using signal flow graph. That means whenever a block diagram is given to you, how can you draw the signal flow graph? So you know that in signal flow graph all variables are represented by node. So here one variable is R, that is that variable means that is that input, and here you have another variable, that is E. Here you can see this is E. Now the next variable is Y3 here, then another variable is Y2 here, so Y2, then the next variable is Y1, so there is another node, and then this is Y, and as this is output node, so then that is Y with that gain 1. So now you can see how that signal flows. So that signal is here, and here you can see that E equal to R minus Y. So here you have that Y. So that means here this is that branch with gain 1. So here you can see applying that signal flow graph algebra, you can write that E equal to R, here that gain 1, R minus Y. So now from here you can see that Y3 equal to, so here you can see that Y3 equal to E minus H1 into Y1. So that means here we are concentrating at that particular node. Now you apply that signal flow graph algebra. So that is y1, that is y3 equal to e minus h1 y1. So here you have another loop. Here you have another loop. Its gain is minus h1. Then you can see that y3 equal to e minus h1 y1. Similarly, you can see here y2. So y2 equal to g1 y3. So that means here there would be one branch and its gain is g1. Here this is that signal g1 y3, and then you have another signal here that is h2y. So that is h2y. h2y means you have, and as there is negative feedback, so you can just write it here minus h2. So here you have one branch with minus h2. So at y2 what you can have, so y2 equal to, here you can see that y2 equal to g1 y3 minus h2 y. So this thing can be represented in signal flow graph. Here you can see that g1 y3 g1 y3, so y2 equal to g1 y3 minus h2 y. Then what is y1? So y1 equal to g2 y2. So that means simple branch with that gain g2. And what is y? So y equal to g3 into y1. So here g3 is that gain, g3 into y1, and you have one path here that is g4 into y2. So that means here you have one branch with gain g4. So this is that equivalent signal flow graph of this block diagram. So that means if a dynamical closed loop control system is represented by block diagram, so from there easily you can find what is its signal flow graph. So this is also one framework by which you can represent a dynamical system signal flow graph. So now we are interested in to find what is the transfer function from RS to YS, and here we will be applying the Mason gain formula. So first thing is you need to find what is the forward path. So one forward path I can see here. So this is that forward path. So is there any other forward path? Yes, there is one more forward path, that is this one. So this is that forward path. So two forward paths are there, and you can see how many. So if this is the first forward path, so the first forward path, that loop gain is, so that forward path gain is g1 g2 into g3. So this is that first forward path, and how many loops are here? So here is one loop, this is one loop. Is there any other loop? Yes, you can see here this is one loop, there is one more loop here, this is one loop, there is another loop, this one. So you can see that there is no loop which is actually is a non-touching loop with respect to the forward path transfer function. Forward path, so the forward path is this is that first forward path, and its gain is G1, G2 into G3. Now let us see what is that second forward path. The second forward path is this one and this one. So that means this is G1, G4. So in this case, the delta 1 and delta 2, they are 1 because there is no non-touching loop. So now we can see here 1 minus, if you see the Mason-Gens formula, so the Mason-Gens formula states that this is delta, so delta equal to 1 minus then sum of all individual gains of the all individual loops. So here how many loops we have identified? There are 4 loops. So that is 1 minus the first loop is say G1, so G1, G2 and this one, so that is G1, G2, H1, and the second one is that G1, G2, G3. So here you can see that this one, this one, this one, this one and this one. So G1, G2, G3 and minus here. So that is minus G1, G2, G3. So now there is another loop, this loop. Here you can see G2, G3 minus H2. So this minus I have already written here. And another one is there, that is G4 into H2. So that means this loop G4 into minus H2. So that is G4 H2 minus is here. And another one is that is G1 G4. So here you can see that this is another loop. So this loop I am just using the yellow color here. So this is another loop. So that is minus G1 G4 minus G1 G4, and here minus 1 is there, so that is minus 1. So these are the all individual loops, and here from this particular signal flow graph you can see that there is no 2 non-touching loops or 3 non-touching loops. So that means we can stop here that delta. So now if you just write it, so you have G1 G2 G3 plus G1 G4 divided by this whole expression, that is 1 plus G1 G2 H1 plus G1 G2 G3 plus G2 G3 H2 plus G4 H2 plus G1 G4. So this is the transfer function from RS to YS. So that means if you have a block diagram and if you are asked to find what is the transfer function from RS to YS, we have already discussed in detail how to find the transfer function from block diagram, and this is another method. You can draw the equivalent signal flow graph for this particular closed loop control system presented in block diagram form, and now you can apply Mason-Gens formula and can directly find what is the transfer function from input to output. Similarly, you can find what is the transfer function from RS to ES. That means if you are asked to find what is the transfer function from RS to ES, you can easily find. So just like the first example, that means here you need to find that you need to make that this node as output node with 1. So this is ES, Now you can see that this is that forward path, and you can apply the same method what we have done previously. That means if it is say ys rs by es, so in this particular example I am just writing here, so I would suggest you all to do it on your own. I am just writing the transfer function. H2 divided by the delta. So this is the delta. So this is the delta, and if you just write it here, that is G1, G2, H1 plus G2, G3, H2 plus G4, H2 divided by delta. So this is the transfer function from RS to ES. Here you can see that in the block diagram, reference command to error signal. So now if you are asked to find what is the transfer function from error signal to output, yes, you can apply that Mason's formula. That technique we have already discussed. That is, if you are asked to find what is the transfer function from ES to YS, so you can write that YS divided by RS, and here again ES divided by RS. So you have already found out what is the transfer function from RS to ES, and this one already you got. So now if you just divide these two, so delta will be cancelled out and your transfer function would be G1, G2, G3 plus G1, G4 divided by 1 plus G1, G2, H1, G2, G3, H2 plus G4, H2. So this term is this one, and this one is this one. So from this example, what we have seen, that means whenever you have a closed loop control system represented in block diagram form, you can get it in signal flow graph framework, and then directly you can apply Mason's formula. And here I have shown how to apply Mason's formula to find transfer function between two variables. If one node is inside that signal flow graph, how to find it we have discussed in detail. So now we'll take one more example. So that is very simple example. That means if you have a signal flow graph like this, so suppose you have this variable and this gain is 1 here, and this is y2, this is y3, and here, okay, so you have this node that is y3, and here you have that 1 gain. Here this gain is G, and then suppose it has that self loop and its gain is GH. So now if I draw another signal flow graph, which is this one, this is that signal flow graph, this is y1, this is y2, this is y3, and this is y3. Here this is that output, this is that input, and suppose you have that this is one branch here and this is G. So now the question is are they equivalent? So the answer is yes. Answer is yes. How? You can see it here for the first case, say y2. So in the first case here, y2, equal to y1, and then it has that self loop, that is y2, and then you have another algebraic equation, that is y3 equal to g y2. Now for the second one, what you can have, you can see here that y2 equal to y1 minus hy3, and here you can see that y3 equal to g y2. So if you just replace it here, then you have that y1 minus this is y2, and then you can see here this expression and this expression, they are same, and you have that y3 equal to g y2. So that's why this particular signal flow graph and this particular signal flow graph, they are same, although they look different, but they are same. So now in this part 3, what we have discussed, we have just taken 2 examples. The first example is if you have a block diagram, how to find a signal flow graph, and from there using Mason-Gaines formula, how to find the transfer function. And the second one is if you have 2 signal flow graphs, they may be look different, but they may be same. So you need to just derive all algebraic equations. From there you need to conclude whether they are same or not. Thank you.